comes
Yeah,
with
so you
it.
have
Oh,
Windows
you wanna
Crown
play with that?
package installed.
Yeah.
That's because they
I used to have that.
Well,
I
I
but
keep
haven't-
needing
haven't
to switch
reinstalled
it was-
yet.
keep needing to
it
switch
was
to
wrong.
Firefox,
Before
but
you guys were in the building you're in now.
when I use it
They're
for
across the
work
street.
and I
You
crash
got,
a tab, I crash everything because it's not process
They fixed that.
isolated.
He talked about.
Did they?
Yep.
Because I heard that and then I tried it
Yeah.
and I still
They
didn't.
fixed it in beta before, but now it's in
You
release.
with them on Swanson?
I might have to retry it.
Something?
Yeah. I would definitely
Because
recommend
I
it.
like that I could install ad block on my phone.
Them, huh?
Fighting over.
Get some of that corn.
Yeah, literally, one of the scrum
Fijian corn.
my two favorite scrum
So when you
teams
see
is
some
corn
crazy
decay
doctor
and
stuff
then
on
it's
Double
rough
Work.
under.
Oh, really?
You
All right.
have to shim
Do you folks have a desktop yet? I just want to make sure that the slideshow's showing up on the desktop.
We're not logged in, but if it's showing up in
I see.
OBS, you should be
very
fine.
scenic picture.
Yeah,
I see
you're
it.
good.
Okay. All right, so we're going to get started. I apologize in advance for any camera flights. Jim, I hope you found the URL and had patience while we got set up. But we're going to get started now. So tonight we're going to continue something we started last week with the Raspberry Pi. I did a few basic things with the LCD. This time we're going to get a little bit further into it. So just a little bit about myself for the new folks. I'm a software engineer at Williams. I've been doing Java for about 16 years, programming for in excess of 20. And I also mentor the Jenks robotics team's programming portion of it. That's where my interest in doing this embedded stuff is. So we're going to jump right into it. And the slide's hopefully visible on the live stream. The premise here is when you're doing IoT, it's all about your input and output capability. And the Pi gives us a few different mechanisms. There's actually a couple more I didn't bother to list. But you've got GPIO, which is the general input-output. That's where you can control a pin and make it hot or high or low. You use that a lot when you're trying to drive things like relays or do something clever, shall we say, with actuators. I2C or I2C, depending on your preference for saying it, is the serial bus. It's not the fastest bus in the world, but it's awful convenient when you're working with little peripherals. Yes?
It's the most convenient feature of it is that it can be chained, right?
Yeah, it is. It's also in here later on.
Oh, it is.
You can have up to, on the Pi, when you do the list of available device slots, that it shows 117. Should be 120 something, but either way, you can do a lot of devices. The big gotcha though is people see, oh, I can do 100 some odd devices. Number one, any given type of device you buy is probably only going to support a couple of addresses, and each device on the bus has to have a unique address. Still, having said that, for most people's purposes, it's going to be more than adequate. You're going to run into problems with wire length before you get anywhere close to 100 devices on it. It's something you have to worry about is electrical interference. Twisted pair works well. Shielded doesn't hurt if you're trying to go for any long distance. I can actually induce noise on the demo unit, which I'll show you in a little bit, just within a 6-inch radius, just by touching it wrong. So, but if you set it up properly, it's going to work reliably. It's just you have concerns about length of distance and speed you set the bus to. But that is my favorite peripheral bus for working with the Pi with. SPI is another perfectly good serial bus. It's actually faster than I2C. But the big deal with it is it uses 4 wires instead of 2. And you really can it's only meant to support on the Pi 2 devices. One of those wires is a chip select wire, and there's only 2 of them. Now you can do tricks like start using the GPIO pins, and you can game the system into letting you do more than 2, but by default it's 2. It is faster than I2C, so if you've got more data you have to push down the wire, you could consider that. Then there's some other ones that have been around for quite a while, obviously. Serial/TTL. The Pi has a serial port. By default, it's set up as the console for the Pi. However, you can disable that and it'll have a normal UART connection for doing serial type communications with. And then of course there's the good old USB bus. That's also serial. It's also much higher speed than anything else on the Pi. Having said that, you have to have something that knows how to do USB communication. So I already spoke to some of these. The limitations are I2C, I've gotten it to work up to about 3 feet reliably. SPI, I've had actually more problems, but that may be due to cable issues that more than anything. GPIO, I haven't actually tried to push the distance on that, but it's limited basically by the voltage that you can get out of the Pi for the distance. The GPIO pins on the Pi are 3 volt, they are not 5 volt. A few of them are 5 volt tolerant. Primarily the I2C pins are, all of these pins that are on the Pi can be really just about used as a GPIO pin. By default, some of them are reserved for SPI, some are reserved for I2C. The I2C pins, if you hook them up, there's been 2 different generations of devices or peripherals for I2C. Some of them are 3 volt, some of them are 5 volt, and rather than blow out your pins on the Pi every time you hook up the wrong one, it's 5 volt tolerant on those particular couple of pins. Which is good. Yeah, it is nice. Otherwise, I would have gone through a lot of Pis by now. Alright, so I'm going to go through today, I'm going to haul out the LCD. We're going to be using it at one point to actually output information from a bunch of the other stuff I'm doing. It's just a convenient mechanism. It's not necessarily won't necessarily scale well, but maybe I can do something about that with this camera. I've got an analog to digital converter chip. And this particular chip is hooked up through SPI. So I've got an example of how to talk over SPI to a chip that allows me to have 8 analog inputs on the Pi. And I have think of it as a volume control, a 10K pot hooked up to that. And we can pretend to adjust the volume. In reality, you could use that for feedback on a joint or angle sensor, or you could actually use it as a volume control, a nice, old analog style volume control for your Pi if you wanted to control like MP3s or whatever. GPIO, I've got a relay board. I think I heard some of you while I was frantically trying to get the streaming stuff set up, noticing it. It's a very convenient thing. SaneSmart makes them. I'm sure other people do too. But it gives you 8 relays on a board, and it has a nice feature to it. It's opto-coupled. And I may have said that wrong, but essentially what it means is the pin coming from the Pi does not directly drive the relay coil. Instead, it goes into a chip that optically isolates it from the relay coil so that you don't get electronic noise interfered and sent back onto the Pi pin when the relay either starts up or ends, because there's a bit of a surge there. That relay board, I think right now costs about $15, and you'd probably be hard pressed to buy all 8 relays unless you're willing to go to Alibaba over in China for less. And then I've got another sensor, also I2C. The LCD is I2C, and the sensor for temperature is I2C. So I'll be able to show you hooking up multiple devices to the bus at the same time. Alright, so that's just sort of a graphical representation of what I've got hooked up here. I obviously didn't try to put it in all the pins. It wasn't my usual self stealing pictures from other people's presentations, so I actually spent some time and drew a crude diagram. Alright, so we'll start with the LCD with the I2C backpack. And I'm going to switch it over to the camera here. See if this works correctly. And I need to turn off the screen capture, otherwise you just see that over it. Okay, and let's see if using this I can get over here. Yeah, this is gonna be easier said than done, I think. Alright, so right now there's nothing on the LCD. When I start running the code, we'll see some stuff on it. But if we look at the back of it, there's a little daughter board that's hooked up to it. Without that daughter board, you'd be using either 4 or 8 pins off your Pi, which is just a lot more wires. If you think I've got a rat's nest on here now, you should see it when you're trying to directly drive the LCD. It can be done. It's easy to do, actually, but this little backpack lets me hook up. I could have multiple LCDs hooked to the Pi. You want to drive?
Yeah. Figure that way you can run the code.
The video will be about 30 seconds behind what we're seeing here. All right, so that backpack right there is a special chip that talks I2C, and it basically gives you, I think it's either 8 or 16 additional GPIO pins. And that's one way of getting additional pins if you need to. There's only so many pins on the Pi. All right, I'm going to take it off of video now for a moment, although I'm going to have to swap back and forth. Not an ideal layout. I should probably set up on the other side. All right, so we're going to switch over to screen share again. Oops, cancel that. Turn on. Turn off. Okay, the video's off. Okay. Now, I'm not sure how clear the video is, or the screen is in the video share.
Be able to hear you over there.
All right. Hopefully people can see the editor. All right, so I've got a few classes in here. Some of it's code I took from the examples in Pi4J. And in point of fact, 2 of the classes that we're actually using were classes I wrote for Pi4J. And they're actually contributed and accepted back into the main project. So the I2C LCD was a class I wrote. It was derived from the original plain old LCD display one. But this one works over I2C. And the temperature sensor, the Temp 102, that's mine as well. I mean, they're nothing super complicated or anything like that. But I'm going to start by running this Hello World program. And I'm going to be doing it from my laptop, even though it's running over on the Pi, just because it's real easy. I don't have to monkey around with command lines and stuff like that. All I'm going to do is change which class I tell it to run, and then NetBeans is going to deploy the updated code to the Pi and run it on the Pi.
Yeah, well, I'm already probably 45 seconds to a minute. I still have.
If you're on your phone, they're going to double it over as so buffering for device. So your device is probably, since you're on a phone, it's probably gonna.
Okay, so it's running at this point, and figures. We've got an actual error that's occurring on the I2C bus. Probably wasn't kind of it moving it.
Yeah, it's quite a buffer then.
I see what's wrong. That should do it. Let's try this again. Keep trying to click on the little picture of the video I've got over here.
Wi-Fi is too-
No, I mean, that's not connected, that's why.
Hmm.
Why it's not connecting, I don't know.
Yeah.
I know this one was still running.
Let me turn off Wi-Fi just for that.
still having an error. No, it's talking to the main display. It's this one that it's yakking about.
Try out 4G and see what we get.
Okay. Is the temperature actually reading now, or not so
No.
much? Nope.
One of the guys,
There we go.
yeah,
These are loose.
you should see some of the stuff he's doing now.
Okay. If we can get the camera on that LCD display. And I'm going to switch over to the camera. There we go. Okay. Can you angle it down a little bit? Might have to turn the contrast up on the LCD. 'Cause you can't really see it. There's a brightness pot back here.
That one? No, wait. Is it that one?
Yeah, it's that blue one.
Okay.
You got a picture real quick, Clyde.
Not too much. How's
that's
that?
good.
Sometimes it's switch.
Want to go double check that?
I'm gonna double check that. All right, so hopefully for those of you playing along at home, you can see the display there. Now you're catching the reflection of the ceiling light.
I can't see what the camera's seeing.
Angle it downwards. See
I'll
that?
tell you what.
Oh, there we go.
Angle the LCD
Yeah, it was
down.
a good idea. Yeah.
There you go.
There we go.
Okay, so what we're seeing here is the Hello World program working. And over here we've got the host name. We've got the current setting of that potentiometer, which I'll show you in a second. And then on the right-hand side, that 76 is the temperature in the room. And then we've got our current IP address.
Don't steal it.
Now, you should see, if I turn this potentiometer, it should go between a range of basically 100 and 0. So that's the volume control knob if you want to point it at that. We got Alexa doing the camera work for me. And, all right, so I'll get back to the code and we'll go through what's going on here.
Yeah, it'll do it. What is it, HTTPS?
Okay. So what's going on in this Hello World program was an attempt to basically run everything except the relays. So it started out as one thing and I kept adding to it, and I've got slides that'll show you more individually what's going on. I'll bring those up, it'll be easier to bring them in. Okay. All right. It should be publicly available on YouTube. The folks here were
Yeah, if you search for Tulsa Java, you can find it. That's what I did earlier.
trying to get this to let me resize the... Oh, I'm actually controlling it inside the thing. Huh. That's weird. How do I make this so it's not as wide as it is? There we go, I got it. Alright. So now if... Oh crap. We lost Chrome. I think that means we lost the feed.
Is the stream still, is OBS still running?
OBS is still running, yes.
Yeah, then you should be fine.
Okay,
So you, it's kinda like me when I
Yeah, you're
hear you
good.
all work at a
Okay.
conference and I log in, you know, my desk.
all right, cool.
That was
I don't wanna resize that though. You still got the top bar cut off in OBS.
Well, what I was trying to do was get this over. Okay.
And then saving it for stuff.
So drag it up to the top of the box and then resize.
The stuff I'm working on.
There you go.
All right. So hopefully everybody's still there, and I didn't drop everybody. I apologize again. This is the first attempt at doing this. The first bit of code that we've got is how to write to an LCD. And it's actually really quite simple. Basically, you import you import a couple of classes, and then it's 3 lines of code. So the first one's just about initializing the LCD display. You do that once, it's there, you don't have to play with it. The next 2 lines show basically manipulating the contents of that. Pretty self-explanatory. You can move the cursor to home, which is the upper left corner of the screen, and then you can write information. Any string you want can go through this LCD write command. All right, so after the LCD, apparently this isn't presenting. There we go. We've got the analog to digital converter. That's the little chip right there that is doing our volume control for us. Code's a little harder on this one, mainly because the analog to digital converter looks like an extension to the Pi's GPIO pins. It basically gives 8 analog capable pins to the Pi. So the way Pi4J handles this, why is it doing that? Oh, I know, it's the edge detect. There we go. The way Pi4J handles this is by plugins, and basically there's a MCP 3008 GPIO provider, and then there's a 3008 pin, and those can be used as a normal pin like you would for a lot of the Pi4J stuff. So what we've got to do in our class is a little more work, but not a lot. Basically, you create a GPIO controller by asking the factory for the instance of it, and then you create an ADC GPIO provider by newing that and telling it what SPI channel you're on. It'll be either CS0 or CS1. That's a one-stop deal. Once you've got that boilerplate code in, you don't have to worry too much about it. Now we're going to create our pins, and I've just called mine input here, and we provisioned it by handing it the provider we just set up for the MCP 3008, and we hand in a constant for which channel we want. So I told you it provides 8. In this case, I'm only using channel 0. It's 0 through 7. And those are constants. You don't have to remember them. You just have to, use your code completion to get it for you. And you can give it a name, which can be useful later on when you want to look things up or enumerate over it. And then below this, you'll see I have edge detect, unfortunately, on my touchpad, and I keep bumping the edge of it so that it scrolls. So I created a little method here called getADC, and that's just to simplify converting it to a string for me. If I remember right, the LCD can take other stuff besides strings, but it was just easier for me. The other thing I'm doing in this is I'm scaling down the value because the LCD had very limited space on it. It's normally between 0 and 1,000. I was trying to get it down to 0 and 100 so that I'd have 3 digits. Space was really that close. Essentially, that's what's happening in the Hello World program. We'll get back to it in a minute. It's just, this is the distilled part that's just the analog to digital converter stuff. The Hello World program that I'm going to go back to showing you in a minute has all the different examples sort of merged together. Then we've also got a relay board. I have with me a robotic arm that I've used in the past that if time permits, we can consider hooking up to the relays. But essentially, a relay is an electronic switch for somebody who doesn't know. We can cause it to turn on and allow power to flow. And this way the Pi doesn't have to try and power the robot's motors directly. So in this case we've got 8 of them, which is actually 2 fewer than I need to control every degree of access on that robot. Because that robot has a rotate command, it has a shoulder, up, down, elbow, up, down, wrist, up, down, and then a claw, open, close. So I'd need 10 to do everything. But it'll be good enough for our purposes. Now, this particular example right here is just going to set up 8 GPIO pins, and it's going to loop through them with a 500 millisecond pause in between and toggle their state, because that relay board you'll hear it click and it has a light that turns on at the same time, so you'll just get to see it march down. I mean, it gets across the point of what we're doing. You'll notice in this example, I'm starting off, when I set up all my pins, I'm starting off with it high, because the relay board is something you'll encounter when doing Internet of Things type stuff. It's what's known as a sink as opposed to, or a drain. Instead of sending a positive signal to the relay board to get it to turn on, you actually ground the pin on the relay board. And this has a couple of advantages, and I'm hardly an expert in it, so people feel free to say I'm an idiot, but from what I understand, it's easier for the chips on the Pi to act as a sink. They can handle a little bit more current that way, as opposed to if we were trying to drive it high, it takes 30 milliamps or 20 milliamps per signal, and if you're trying to turn on all 8 simultaneously, you're drawing a lot of power through the Pi. So a lot of these things are set up so that you actually want to drive them negative to turn them on. And that's this line down here. All I'm doing is a mod on my loop counter. So up here I've got a loop that goes through from 0 to 63. And whatever that counter is, I'm modding 8 so that I know which pin I'm turning on, because I'm doing more than one iteration through. Oh, we're not quite that far yet.
Why? I was looking at the constants in the middle there.
Mm-hmm.
GPIO underscore 23,
Mhm.
25. Just wondered why they were out of order. Is there a reason, or is it just?
Yeah, it comes down to the fact of where I plugged the wires in. So first off, some of those wires are on one side of the header, some are on the other, and I wasn't paying close attention. So what I did was I got them all plugged in. I ran through this iteration of marching through, figured out which ones were not in order, and just changed the order.
There you go.
Easier to change software than hardware.
Exactly.
Awesome.
So, it's not for any real scientific reason or anything like that. I will show you how to get there is a different number of pins on the different versions of the Pi. I'm using a Raspberry Pi 3, which I believe gives me an additional, 16 pins, something like that. It's a longer header than the Pi 2 and the Pi. But back to this, because we'll break off into code. I'm almost through the slides. The Temp 102 sensor, and I'll show you on the camera, and you guys can see it in the room. It's a little bitty thing. Basically, if you look at the right-hand side of that screen, that tiny little black dot dead center is the actual chip. All the rest of that board is just so we've got a nice place to solder to. But the nice thing about it, I've used temperature sensors before. One of my kids' science fair projects was monitoring insulative properties of different materials. So we did it in the winter, and at the time I had an Arduino. We bought a bunch of analog, resistive type temperature sensors. And so I had, like 10, 12 long wires with a little tiny thermistor at the end of it. And we put them in these boxes and lined the boxes with different materials, and we put it outside. But the thing with the thermistors, getting them calibrated is a royal pain in the butt. The nice thing about the I2C thing is there's not as much for me to do. I ask it, what is your temperature? And it tells me, as opposed to me trying to divide voltages and make sure, because depending on power fluctuations on my source and how good the regulator is on the board, 5 volts may be 5 volts or maybe 5.01, and it could affect the reading on a thermistor. You can compensate for it, but this one's just plug in. Yeah, no math here. No math here. This one's nice. You just say, hey, how hot is it? And it'll tell you in Celsius, and if you want it in Fahrenheit, go ahead and convert it. Because it'll tell you in Celsius. Now, working with this example is a little more complicated because I chose to leave the LCD code in as well. And what I'm doing in this one is I've got this typical setup for the LCD display. I create a new temperature class, and I pass in which I2C bus I'm on. On the Pi 3, it's bus 1 is the one that the pins are visible for. I think it's on the Pi and possibly the Pi 2, it's bus 0. So you do have to be cognizant of that. And then that last parameter you see is the address, that 0x48. That is the address this is set to. It can be set to an alternate address. It supports 2 different addresses, but I'll show you how to detect those type things in a second. There's a command line utility that's available on the Raspbian distribution. But the reason I left the LCD stuff in here was I wanted to take the opportunity to show one extra thing. You see how I'm homing the cursor, and then I'm writing the network info, get host name. Okay, this is all before the loop. And then I just put myself into a never-ending while loop. This set cursor position allows me to set row and column that I'm going to write to. And the reason I do this is if I set it home and then I replace all 2 lines of text, you get this flashing effect on the display. But if you just overwrite a couple of characters that are changing constantly, you don't get that. So you can have a nice responsive thing without rewriting the whole display every single time. And to tell you the truth, the get temperature scale Fahrenheit, we're actually doing the conversion in the class I wrote for you. So while the actual hardware only sends it back in Celsius, we have a friendly converter for you.
That looked like a tight loop, but maybe there's some inherent.
I didn't even
Slow
run it.
down?
I didn't even run it because that was just meant to distill it down to an easy to
Okay.
understand thing. When we get into the real code in just a second,
Okay.
you'll see
Yeah,
I've got sleeps and stuff like that. All right, so I'm going to pop out of this. No, I didn't really want another tab. Here we go. And that's reasonably visible up here. Okay, so the hello world that I was showing you the display for is all right here. We're doing everything you saw in those individual examples except for the relay stuff. And I have one final example afterwards, which is responding to essentially a button push, like a doorbell or what have you. But all the initialization in the hello world we're running here, we're actually printing out the host name, the analog to digital value of that potentiometer, and we're printing out the temperature. And then we're setting the cursor position to 1, and we're writing out get info, which, if I recall correctly, I've got a little method down here that basically finds the non-127 IP address. The number of times I've come to one of these things and done a presentation with the Pi and not known what the IP address was what made me want to print that out on an LCD display, so that if I set this to run at startup, it's going to tell me what IP address it's on, if it's got one. Now, let's see. I've run for you the Hello World. We've got the display showing it, and we've played with the temperature and the analog value. So next thing I'm gonna run for you is this control pin, which is similar to what we saw on the slide. Stop this. Let's switch the broadcast over to the camera again. Okay, and if you can just take it so that you can see the relay board. That's perfect. Okay, so I am going to hit run, if I can find my cursor. Here it is. And what should happen is it should just march through those relays. And we'll go through the code in just a second. What couldn't you read?
I can read.
Still connecting to it. Hang on a second.
Can we get a copy of this?
Yes, sure. Try it one more time. I wonder if we're having trouble with the network now.
There we go.
So that should show up on the live streams if you guys have that. There you guys go, look up at the screen.
It's a very nice noise too.
How fast can they switch, since they're the light kind? Can they still switch pretty fast?
Yeah, they can switch reasonably fast. I mean, you're gonna probably be more limited by the electromechanical action of the relay than you are the optocoupler.
Or even the I2C bus, I would bet.
Yeah, the I2C bus is running at 400, well, this isn't the I2C bus, this is direct GPIO.
Oh.
What about all those buses? I mean, are they all super fast or?
They're faster than anything you need. So for instance, with the temperature, it's sending back like a byte.
Right.
And it's running at 400 kilohertz.
The GPIO, I think, were stress tested at several thousand hertz.
Oh, okay.
Yeah,
So-
you're going to
So
be
you do-
limited by the actual mechanical
Yeah.
switch in those.
Gravity and Newtonian physics.
Well, just acceleration and magnetic induction
toggle.
forces.
In fact, even before the bus, you'll probably have problems with most programming languages not being able to keep up.
No, I'm pretty sure.
Well, yeah, I mean,
there's
if,
your bottleneck.
even
is
if
the
even if
switch,
you don't
not-
include
not
the
any of
switch,
the rest of it.
but even if you don't include the switch, the bus itself is going to be faster than what the CPO can process instructions at.
So, I mean, I know it's not horribly exciting, but you can definitely hear that it's creating an action. And what we've got, if I've got the time and we can get the wires to cooperate, is an old ARM kit I bought some years ago. And essentially, it's got one little thing broken off of it, and you can see it's dust covered, but it's kind of fun. And what I haven't done is I haven't put any feedback mechanisms on it yet, so it's blind. But
So you'll get a
simply
lot
by
of
shorting a
grinding
couple of the
gears.
pins, what?
So you'll get a lot of grinding gears if you're not careful.
Yeah, you don't want to run it.
Oh, I saw it.
It's even got a little light. Where was it?
Good little robot, right?
I've got a picture with the pinouts. I figured this out the other night.
It doesn't do much right now.
So what we're going to be doing with those relays is essentially shorting pins together on here that allow the motor to run. Now I have another board that I did not have time to get set up and work with, but this is also an I2C board. Maybe I should have gotten it set up and then I could have used it to control the pan and tilt. This board right here basically is a servo controller board. It lets me control 16 servos. The nice thing about difference between a servo and what was in that robot arm, the robot arm's just a plain old motor, a DC motor on gearing. The servos that you can see right here has a motor, but it also has feedback positioning built into it. So you send it a PWM signal, pulse width modulation, and that essentially means you turn the pin on and off at a certain frequency for a certain duration, and using that tells this to move it to like 10 degrees or 90 degrees. Typically these have about 100-degree range of motion. So with this, you can set, this is meant to be a pan and tilt for a camera, a webcam, and so that is one of the things I'll be setting up with this. I've set that up with the Arduino before, but this will be the first time I've gotten it going with the Pi.
So why, I think this is off topic, but why a servo over like a stepper motor?
Well,
One of the Gs, one of the other.
a stepper motor requires more pins. Okay, so depending on, I forget what the actual term for it is, but basically the step size. It basically is indicated by how many coils there are in the stepper motor. So to get it to do a full rotation, you have to energize the coils in succession. So you'd have to use a lot more outputs. They're very nice, they're very precise. That doesn't mean you can't cause them to skip, and you won't know about it in your computer program, because if you actually force advance it, there's no feedback mechanism. It's very precise on how, if you say turn 100 degrees and you send it the right number of pulses and you don't overload the motor, it'll get you there and it'll be fine, and it's only limited in speed by how fast you energize those successive coils. With the servo motor, it's going to self-correct. So if you force it beyond, as long as the overload goes away quick enough, it's going to come back to, you're essentially saying go to 90 degrees.
Okay, so it'll go.
Basically, it's got a potentiometer, a little one built in to the servo, like what we've been playing with on the ADC, and it's got a little ADC board on there, and it's just a little tiny circuit board in that thing. So you basically are telling it. And some servos actually can maintain a signal. So in other words, you send it, go to 90 degrees, and you don't have to keep sending it the pulses to get it to 90 degrees. You just, the nice thing about that board right there is it works that way. The servos, those servos are cheap, they don't know how to do that. But that board I just showed you,
Right.
I can say go to whatever position, and the board maintains the pulse rate for to put the servo where you want.
So you send another signal.
And with 16 of them, you can do quite a bit.
And of course, the stepper motors, you can put your own encoder on it and stuff to
You
get
certainly
them to
can.
do that. But that's something you got to do.
Right, you can do that with motors too, and in point of fact, in the first robotics challenge we use encoders quite a bit. We use them an encoder basically is a sensor that goes on the shaft of the motor or the gearbox, depending on your needs. And it tells you how many revolutions or how fast it's spinning. And you use a formula called PID, and gosh, I didn't expect to talk about this tonight, so I don't remember what the initials stand for.
Partial integral derivative.
Thank you. It's a controlling mechanism, basically, that you plug in the right numbers into it, and it follows a formula so that when I say go to 90 degrees, it doesn't go full speed to 90 degrees, because
Oh,
they don't
ramps up,
stop that
yeah.
precisely. You want to, as you approach 90 degrees, slow down and try not to overshoot. And if you do overshoot, how quickly and how hard do you correct back? You get that formula wrong, and you wind up with oscillation that can actually get bigger with each swing. And if you get it wrong in the other direction, it'll take forever and never actually achieve the state you want.
And may not ever actually reach that position.
Right. So I've watched a bunch of videos to wrap my head around it, because we had need for that in the robotics competition. And I've seen it described by some very brilliant people as half science and half art form, tuning those constants. There's strategies for how to arrive at close to the right numbers to plug into that formula, but it's a lot of trial and error too.
Ultimately, it's going to be different for each situation.
Right, and actually you could have 4 different motors of the same type and manufacturer.
I need 4 different formulas.
Well, not formulas be the same, but you might have
Values.
slightly different constants depending on, maybe one has more friction or something stupid like that, Sounds like you've used it before since you knew what it stood for.
I did 3D printer worlds for temperature and stuff. I recently found an Arduino library that I use to control, actually my spindle speed on my small CNC that I got, so. Yeah, just into constants took a while. I should have used their auto tune. Did it myself.
Used it in Kerbal.
Finally worked.
So, having said all that, let me go back to the code.
Suppose you could interrupt a command, like if it was in the process of going 90 degrees, and you got into it halfway, you could send a command to tell it to stop, or change direction, or.
Well, it really depends on the control mechanism, so if your motor controller is interruptible, then sure.
Yeah.
And one of the things that we do, there's a couple of places you can implement PID control logic. So in the robotics competition, they support it in the Rio, which is the computer that is the brains of the robot. And we use CAN bus, which is something the Pi doesn't have, to my dismay. Although I've got an add-on I just bought. CAN, C-A-N. Same bus that's used in your automobile for the various parts to talk to each other. We use CAN bus to control the different motors, etc., because it allows for the motor controllers and various sensors to report back to the central processing unit. So the motor controllers we use are Talon SRXs, and before that we used something called a Jaguar. Both of these supported doing the PID function in the motor controller. It's really nice. You went into you sent a configuration command to the motor controller and said, here's your constants, and here's your sensor to use to tell where you are, and it did it for you. And it offloaded some of the processing from the main computer.
So you just monitor a status line.
You can either monitor status, or you basically can take it on faith and you say, go 10 meters, and as long as you've plugged in the necessary information into the API for the motor controller will go until it's spun an appropriate number of times.
Was it using some kind of line beam break, or how did it know where it was at?
Well, basically it goes by rotations.
So it's literally just keeping track the whole time.
It's keeping track of rotations. So what it doesn't account for is like friction or slippage, rather. So if your tires are slipping, it's not going to know. It just knows it's spun them 10,000 times, or however many times it took to go the distance.
Deviate over time, I guess?
Yeah, well, there's other strategies you employ as well. So you might say, go 5 meters, and then stop. And there's other guidance systems, like you can use gyroscope, accelerometer, and those will tell you if you've drifted to the left or right. And
Ultrasonic rangefinders.
yeah, which are surprisingly inaccurate, but yes, they're
So
good to avoid hitting stuff.
Kludge them all together though to get your
Yeah, there's no
location
one
data.
thing that gets it for you, but you'd be surprised at dead reckoning and time does.
On one end.
A lot of times at the competition, you've got 6 weeks to build this thing, and they don't usually have the design for the physical robot done until like week 5.5. So you're sitting there frantically trying to code, and half the time the fancier logic goes out the window, and it's like, okay, the competition has an autonomous mode where you get so many points for moving from one starting point into another zone. Well, okay, if I run the motors at half power for 5 seconds, I'm almost definitely in that other zone.
Okay.
So
You start budgeting.
you got all these fancy sensors, and you wind up using the dead reckoning system. So, all right, let me get back to the NetBeans here. And turn off the video capture. All right, so where's my
Gaming the
cursor?
system.
Sorry, what?
Talking about gaming the system.
Yeah, well, it's not. It's entirely valid, but I mean, you've got all the other sensors. I actually took the time to get
It's the
encoders.
value of what's being measured.
Yeah, I actually took the time to get the encoders understood for this season, and we still didn't wind up using them like we thought, because the one system that they worked really well on, the launcher, got left off the robot because we had too many problems with the other systems. So, you know, it's a new thing every year. All right, one of the things in the slide deck, which when I share it, you guys will see on those examples, is I did an import GPIO star, or I used the asterisk, and that was really because the slide's fairly short. You can't fit a lot on it, so I didn't want to waste half my slide with the individual imports. However, I don't usually recommend that. It's just a style choice more than anything. I'm just trying to explain the difference between the code and the slide deck. All right, so here's a line that's new as of the most recent release of Pi4J. Prior to this, if you wanted to access the GPIO pins directly, you had to basically run as sudo because of the kernel, the Linux permission system. There is something in the kernel now called the device tree, and it allows them to mark certain parts of the hardware accessible without root. And Wiring Pi, which is the underpinnings for the Pi4J, added support for this, so Pi4J was able to add support for it. Basically, you have to call this enable non-privileged access, and the reason you have to call this is simply because they do not have non-privileged access turned on for PWM, and I forget the reason they told me. It's on one of their blogs, but there's some reason it's not quite right yet for PWM.
You can end up overloading the processor and forcing it to lock out other applications, so.
Sounds reasonable to me. For one thing, PWM on the Pi is not your best bet. You're mostly doing it in software. I think there's supposedly one pin that has hardware support for it. But considering the fact, the frequency you're toggling that pin on and off in software, the Pi is not a real-time operating system, so you're not going to get as reliable results as if the hardware is handling it for you. If you want to do PWM, you're better off getting a board like that one that I just showed you with the 16 outputs, and the hardware is doing the PWM. I'm just telling it, hey, run at this rate, and it handles the timing on it. It leaves my CPU nice and free. I can do other stuff, you know, folding at home or whatever, and not break a sweat. But for anything else where I'm just doing something simple like the direct access of the pins to turn on or off the pin, you can set this command line right here, the GPIO enable non-privileged access. And if I do that, I do not have to run my Java program as sudo or set UID on java.exe or Java, not exe on Linux, but you know what I mean, which is always a bad idea. All right, so we talked about in the example, this is pretty much the same thing. You know, we're creating an array of pins, and you don't have to create an array of pins. You can just create 1 or 2 pins and hold on to them. I was doing it so that I could iterate over them pretty easily. This name can be anything you want it to be. It really doesn't make any difference, but it can be displayed at will when you're checking on the pin. In this particular case, this is the same as the example code. I'm sleeping for a half a second before I toggle something low or high. In the case of when we hook up to the robot, you know, you would obviously not want to do it like this. You would want to react to some sort of like a button push or something like that. So while this button is pushed, set this pin low, and that turns the relay on, and
Do a
then
callback.
yeah, you can do a callback, but I mean, we don't have any feedback on the robot right now. So since the arm has no feedback, I don't have like an end stop switch or anything like that. Could do that. You can put little reed switches or whatever, and all sorts of ways we can trick this out and make it better. But and then the rest of the code's about catching interrupted exceptions and stuff like that. You will occasionally get exceptions when you try to write to different things, and not so much on this general purpose GPIO right here, but for instance, when I was writing to the I2C bus earlier and we had some problems with a loose connection, you'll get an exception thrown. So, you know, you can catch that exception, you can try to recover from it. In my case, I wasn't doing much except printing the stack, but those are things to IO exceptions should be expected and probably handled if you're writing code for this. Let's see. There was one other one. Here we go. This one was not in the slide deck. This is the only one where I've done a react to an event. Okay, so this is basically going to, it's actually one of the Py4J examples, so it's not like it's hard to find. Most of this is all boilerplate set up for parsing command line arguments, so you know, forget all that and let's get down to where we actually handle something. So we've created a GPIO pin digital input, and we're calling it my button here, okay? You notice that it's an input pin. And that has significance because it means we're not going to try to set it high or low. It means we're just going to read from it and ask it whether it's high or low, and that's being influenced by outside events. So, and this pull right here, if I remember right, is internally on the Pi, there's pull-up resistors that you can set whether they're engaged or not. But you asked about, or you mentioned reacting to an event, and that's precisely what we've done here. We created a listener of type GPIO pin listener digital, and we give it the override method that we have to do for a state change. And if we run this, and I short a pin here, you'll see we're going to print out green on our our console or red. And that's about all this does. I mean, it's not earth-shattering, but it does show you that we're not sitting there in a loop, we're not, you know, sleeping constantly, we're not doing busy work and polling. This is a much more efficient way to react. It's an event-driven system as opposed to loop-driven.
Do you think in the background it might actually be polling or?
Actually, there's hardware in the system where when the pin state changes, it's able to trigger an event in the code that's been watched for. It's literally, truly event-driven.
And Arduino has like a pin change interrupts and then standard interrupts.
Is that a get
Exactly.
state?
I'm sorry.
Get state?
Yeah, and we did that because the event came in, and so we ask it what pin the event's for, and then we say event.getState.isHigh. So basically,
Get state's the voltage and is high is a
yeah,
value
it's
they're
just a Boolean
functional,
at that
yeah.
point. It's a way to easily determine high or low because there's sort of gray areas
So
actually.
event is a class.
Yes.
Yes. Yes.
Is it a class that came with the library, or is it a class that you?
It's GPIO pin digital state change event.
yeah, this is the one that came with, oops, I don't wanna actually change this. This is the class that came with the Pi4J library,
Oh, okay.
okay? And the name, we just named the variable event.
That's slick.
Yeah, and there's actually a ton of features that I'm not even going to get anywhere near exploring. We just don't have time. But Pi4J is actually very easy to use from Java. It is not necessarily as fast as doing, raw native C code. But if you want to work in Java and speed's somewhat important to you, there's two levels of APIs for Pi4J. There's the upper level ones, which have all the creature comforts and stuff like that, make it super easy to work with, and they have safety checks built into them so you can't do stupid things as easily. But if speed's more your important thing, there's another set of APIs which are basically JNI wrappers over the native code. So if you call those, you're as close to the native code as you can get and still stay in Java. Because all it's basically doing is a pass-through. I haven't needed that kind of speed personally. The normal throughput is more than adequate for anything I've ever tried to do.
So it's in SE?
Yes, Java SE. I'm just using NetBeans here because I like the remote deploy and running and debugging capabilities. So I'm going to run this, and basically we don't provide any, oh crap, did I forget to stop the previous one? You know what, we lost the output. I think that's the problem. Alright, so it's up and running right now, and I didn't give it any command line arguments, so by default it's going to look for pin 1, I think, if I recall correctly. Oh yeah, you have to change it to here we go. We have to change it over to broadcasting the camera. We're so high tech. Alright, so the problem is we're going to have to switch back off of this as soon as I do it. Or yeah, you have to point it at the screen, whatever. So, was it pin 1 or was it pin... Oh crud, I had a pin... I think it was this one, to tell you the truth.
Or you expect
I think
to
it was
short
going
to?
ground.
Okay.
Okay, yeah, I got it. Okay, so guys up on the screen, when I touch this wire to ground, or it would be the same as if I had bothered to wire up a button and push the button. Okay, so,
Be able to see it through the camera like that.
yeah. All right, so right now it's high. I touch it to ground, it should go to low. I let go, it's high. And the reason why it's going high when I disconnect the wire is because of that pull-up resistor I told you. If I turn that pull-up resistor off, I'd actually be able to toggle whether the state changed. So
Does it handle like switch bounce? Like it can be pretty fast compared to.
Pi4J has some convenience debouncing stuff, but you may actually have to play with that to make sure you got it right. For those of you at home, I don't know if you could see the screen when he was pointing the camera at it, but I'm displaying it now. All those states between low and high were when I was connecting and disconnecting the wire. Does anybody, this is pretty much all I had for my presentation. I can go back to screen here. And I think I just basically had 1 or 2 slides left. Basically, the chief limitation is your imagination, which surprisingly can be fairly limiting.
I thought your limitation was if someone's already made it before.
Not really, you can make it again, it's just a question of, no, I don't really wanna edit it, I wanna present it.
Things like these seem unachievable when you're looking at it, and you haven't even entered into it yet.
Yeah.
But once you get into it, and you actually do something small, and it starts to grow in your head, and it starts to just develop into something bigger and bigger.
Surprisingly, one of the trouble I have personally is
The whole trick is put your head into it and keep it there.
yeah. Well, one of the things I wind up having trouble with is I flip-flop on whether to write the code first or the hardware first. So I wind up trying to flip-flop back and forth between them. And I'm not entirely sure that's the best way of doing it. The other thing, you saw the mess of wires just from doing this little test. And that can be extremely frustrating when you start getting poor results because you've got bad connections and you have no idea if it's because of what you designed versus something's just a little too wiggly. So what I'd recommend is, in addition to prototyping boards like that one, you learn how to solder and you get some perf board, or you learn how to use one of the PC board designers. They're not that hard. If you can draw out a schematic of what you're trying to do, they'll convert most of it into a board. A little bit of effort, and you can send it off. You don't have to, you can etch it at home if you want to, but you can just upload the file to a lab and they'll get you 1 to 10 boards for $10 or something like
There's
that.
a lot of options for really cheap board production.
Yeah.
That you can send it to them, it takes a little bit longer, but they'll get you 3 boards for like $3 a piece or something.
Yeah, it winds up being very cheap.
Which site was that?
I haven't done that since.
Oh, I know, like, for instance, I think one of my students found one, Seed Studio, has a deal where they'll ship you, for $10, they'll ship you at least 3. I think it was actually more than that. I'm not really sure I want more than, if I'm prototyping, I only want 1, but,
Well, you have to get a minimum of 3, I believe, but it's always good to have 3 even when prototyping.
You might solder something terribly.
Yeah.
You might spill coffee.
I know
on
me,
one.
I'm not,
But as you're at home, you get a dork with all this stupid acid and kind of throw it away.
Yeah, what do you do with it?
Well, you have to
dispose of it.
baking soda in it, I think. or
Okay.
put
well,
something
with the
in
acid
it
for the etching, the ferrochloric acid, it's not that strong. I mean, you can actually put your finger into it as long as you don't have a cut and it won't hurt. Wash it off fairly quickly afterwards. But, yeah, like he said, if you put baking soda in small increments, or you will regret it, it will make it inert, and once it's inert, it should be, safe to dispose of.
Just do be careful because it's loaded with copper at that point.
Yeah.
So don't
the
pour it down
copper's
very.
poisonous.
Yeah.
And whatever you do, do not dump a chunk of raw sodium in it. I mean, pure sodium, not raw.
Well, that's bad in plain water anyway, right? But
Yeah.
Well, that's with plain water. It wants to give up an electron, and the acid wants to get an electron. So,
Deionized water.
well, if you jump when I was in 10th grade, one of my buddies, his father was a chemist, so he brought in a little bottle with some sort of oil in it and some actual sodium. I mean, not salt, sodium. And so we took a little piece, and we were in electronics class, so we had ferrochloric acid. So we put a bowl of it in the sink, and we plopped it in, and oh man, that thing split out, flaming and going everywhere.
How'd your teacher react?
He wasn't in the room at the point we did it. We're not dumb. Well, we were, but we were cunning at least.
I do want to say,
So you would do that in even at the end.
since this is on YouTube, I do recommend, just a small disclaimer, don't actually put your fingers in ferric chloride.
Oh yes, that's a good point. Do not try this at home. We're not professionals either, but I don't want to be responsible for somebody getting hurt.
If it's in low enough quantities, it shouldn't harm you,
Yeah,
but
it's
of course,
I wouldn't
You know.
touch it.
yeah, I wouldn't touch it either if I can avoid it. Use gloves if you can.
Follow the recommended manufacturer's instructions.
Exactly.
Don't drink it.
Definitely.
Definitely
do that.
Spoil all my fun.
Have a little more than an upset stomach after that.
Actually, I think hydrochloric's probably stronger than ferrochloric, but yeah, you'd probably have.
Which one, see,
You wouldn't be happy.
when I use hydrochloric acid, is that normal?
I think that's what your stomach makes in small quantities.
Oh, okay, I thought you meant 1,000 for itching.
It's been over 2 decades since I had biology class, so I
Your
could be wrong.
stomach produces hydrochloric acid, that is correct.
Okay, you heard it from our members.
From the expert.
Someone who
He's
remembers
definitely the
sixth grade
expert in
science.
this room.
All right, does anybody have any questions or suggestions